Welcome to the EP450 final video project. I'm Noah Woods, and this is the biomechanical analysis of throwing a Frisbee. For this Frisbee throwing video, we're going to be talking about the main muscles and bones used, along which planes and axes it's acting, the quantitative, qualitative aspects of this motion, as well as the linear aspects of this motion. There are two halves and four major actions when it comes to Frisbee throwing. There's horizontal adduction and flexion, and there's horizontal abduction and extension. Depending on whether you twist or not when you throw the Frisbee, you could be using your external, internal, transverse obliques, and your rectus abdominis when you throw the Frisbee. The major muscles that we use in our arm and shoulder to horizontally adduct and flex the Frisbee during the beginning of our throw includes the biceps brachii, the brachialis, the coracobrachialis, the subscapularis, anterior deltoid, and pectoralis major. The main muscles we use in our forearm during the Frisbee throw include the flexor carpi ulnaris and radialis, the flexor digitorum profundus and superficialis, the palmaris longus, the pronator quadratus or teres, and the supinator. The pronator quadratus and teres and the supinator mainly to just change the angle of the throw. In order to horizontally abduct and extend our arm during a Frisbee throw, we're going to use the anconeus, the triceps brachii, the deltoid, the supraspinatus, the infraspinatus, latissimus dorsi, and the teres major and minor. The main muscles that we use in the forearm when we extend the wrist to throw the Frisbee include the extensor carpi radialis longus and brevis, the extensor carpi ulnaris, the extensor digiti minimi, the extensor digitorum, the extensor pollicis longus and brevis, and the extensor indicis. The major bones that are involved in this motion include the scapula, the humerus, the ulna, the radius, all of the carpal bones, along with the metacarpal bones and the phalanges. And these actions previously mentioned all occur along the transverse plane and around the longitudinal axis. And when it comes to quantitative data, there are a lot of things that are able to be measured when it comes to this action. Things like weight, whether it's of the Frisbee or of the person throwing the Frisbee, or you can measure the displacement of the Frisbee along with its speed, velocity, and acceleration. You can measure the angle at which it's thrown, the kinetic and potential energy. You can measure the wind speed that might affect the travel time of the Frisbee itself, even the arc of the Frisbee if it's thrown at a higher angle and drops to the ground. To further expand on this quantitative data, here we have a shoulder torque, elbow torque, and wrist torque. These combined can form an eccentric force apart from the center of gravity, thus creating from the hand to the center of gravity a moment arm, and this turning motion causes an angular velocity. So we have an actual tangential acceleration caused from this eccentric force, and then we can measure the displacement from the center of gravity of the Frisbee to where it may land. And this causes a force couple, which causes a spinning motion of the Frisbee as it goes through the air. And so you can actually see from this advanced drawing, if you took the height from where the Frisbee was released to the ground, and then even the distance that it traveled, you could possibly create an equation like the Pythagorean theorem to measure the angle at which the Frisbee was able to travel. We can also see here from Newton's 3 laws of motion that an object in motion tends to stay in motion until acted on by another force. This is when the Frisbee's traveling in the air. You cause the force to throw it, and the air resistance keeps it up, until Newton's 3rd law of motion also acts on the force when the Frisbee hits the ground, the force pushing up and the friction pushing back on it as well as your force throwing the Frisbee and the air resistance keeping it up, there's also the force of gravity that is pushing it down as well. So all these forces are acting on it and not letting it continue in its motion according to the first law, and also equal and opposite reaction according to the third law. And you can also take the force of this times the mass and acceleration to apply the second law of motion. Now we get to look at the qualitative data associated with throwing a Frisbee. A few examples of qualitative data that we can look at are things like gender, expertise, training, technique, and style of throw. For example, I would be a male Frisbee thrower. Ultimate Frisbee Club is my expertise. I was only training myself. I was never formally taught by anyone. My technique, I like to just take a step and throw rather than sprint and throw it, and other examples like that. My style of throw, I like to throw traditionally. There are various styles of throw. You can throw with your hand just on the side regularly. You can throw with just your index finger under the Frisbee itself. You can throw with your thumb, again, under the Frisbee itself. And you can even hammer throw, which is where you hold it as such, and you throw it over your head. Those are some examples of qualitative data. Just some final points to conclude this video on the biomechanical analysis of throwing a Frisbee. Normally there is no fluid medium when it comes to this. If there was any, it'd be in rain, and if there was in water, it'd be very difficult because such surface area from the Frisbee to travel in the water, it would not go far. Some internal forces are mainly produced by the muscles used around the Frisbee. The muscle acts as a lever system across the bones, and then the torque around the joints of the angles to pull the force around the Frisbee, causing an external force to act on the Frisbee, which makes it spin. And your stability is formed by the base of support made by your legs. So the wider that you spread your legs, the more support and base you'll have to turn on and produce more torque, produce more force, and throw the Frisbee harder, which also affects its linear and curvilinear paths. The harder you throw, the farther it will go, and the straighter the path it will be. If you throw very softly, it's going to curve in a curvilinear motion. And if you generate more force and throw it farther, it will most likely make a more straight path down to the ground. And if you throw it very hard upwards, that it's going to have to descend at some point. So there will be an arc and a curvilinear motion of the Frisbee.